Okay, so the last of these videos on some proofs that I usually skip over when teaching an abstract algebra course, I'm going to look at showing some things about two elements commuting and a last law of exponents that requires two things to commute. So first of all, I'm going to suppose that A and B, these guys commute. We have a multiplication AB equals BA. If that's the case, then any power of A and any power of B commute. And let me say that if I'm going to show this, I'm going to assume that I have an associative product. And actually, if you're going to be really picky, all I need is an alternative algebra, because I'm just going to be taking two things and commuting them. But let's not worry about those kinds of details. Okay, proof. And by the way, that's for positive exponents. If we want to deal with other exponents, we're going to have to add on a few assumptions. So let's do that in stages. First of all, okay, suppose that A and B commute. Now let's take and show this holds, first of all, that A and powers of B commute. Well, you can see that AB to the first is AB, which is BA by hypothesis, which is B to the first A, okay? So what I just showed is that A commutes with the first power of B. That's my base case. Once again, I'm going to make an inductive hypothesis. My inductive hypothesis is to assume that A B to the n equals B to the n A. This is for some fixed positive B, positive n. Okay, and let's show that this then holds for one power more. Okay, well, we have AB to the n plus 1. By definition, this is AB to the n times B. Okay, well, we have made our inductive hypothesis that I can switch these guys around. So that's B to the n A times B. Then I can use my regular old hypothesis that I can switch A and B around. And then use the definition of exponentiation to get that this is the same thing as B to the n plus 1 times A. And so I've now shown that it holds for 1. This holds for n, implies it holds for n plus 1. And so by induction, we have that AB to the n equals B to the n A for all positive n. Okay. Now, that's not quite the theorem statement. We'll come back to that in a minute. But let me say that we can also extend this. What if we have an identity? If we have an identity, let's say 1, well, then we can talk about exponents raising things to the 0th power. Well, in that case, B to the 0th power is 1, which 1 times A is A, which is the same thing as A times 1 is A, which is the same thing as 1 times A, which is the same thing as B to 0 times A. And so there we go. Our base case holds. Our inductive hypothesis, suppose this holds for some non-negative n. This shows then if it holds for that, holds for one more, and so it holds for all non-negative n. Okay. What about negative exponents? Okay, well, let's suppose now that A and B are invertible. Okay, so that they have inverses. Right. By the way, if two elements have inverses, you can show directly by doing this calculation that AB times B inverse A inverse is the same thing as, well, B inverse is 1, so that gives you A times 1 times A inverse, that's just A times A inverse, which is 1. And on the other side, B inverse A inverse times AB, well, the A inverse is the identity, so this is just the same thing as B inverse B, which is 1. And so therefore, what this little calculation over here shows is not only does AB inverse exist, it shows that in fact it's the same thing as B inverse A inverse, right? We call that the sock shoes principle. The idea that if you want to put on your shoes, you put on your socks, you put on your shoes. If you want to take them off, you take off your shoes, then you take off your socks. To undo something, you undo each step, but in the opposite order. Okay, so that's lying in the background. Let's see how that's going to help us. Well, all right, so we have our base case. Now let's suppose that this holds for some negative power, b to the minus n. Okay, you have to adjust this a little bit. All right, so okay, what do we have? Well, we have a b to the minus n minus 1, okay, because we're gonna go down to a lower power. Oh, actually, okay, yeah, that works. This is a times b inverse to the n plus first power, all right, which is the same thing as a times b inverse to the n times b inverse by definition. My inductive hypothesis says, and in a previous law of exponents actually says this is b to the minus n, right? I guess I could have just used that. I can flip that around. Now I need to know that I can move b inverse past a. Okay. Well, why is it that I can do that? Okay, well, off to the side, let's notice that if we have this assumption AB equals BA, because B is invertible, I can hit this on the right-hand side with B inverse. And this becomes A equals BA B inverse. Then I can take this expression and hit it on the left with B inverse. And I get that this is B inverse A equals, those cancel. So that's just 1 times A, which is A, B inverse. And so kind of off to the side, we have that if A and B commute, and B actually has an inverse, that A will commute with B's inverse. Okay, well, so then we can apply that in our work right here, and we have b to the minus n, b to the minus first a. We can flip those around, which is b to the minus n minus 1a. Okay. And so what we have shown is if it holds for a negative n, or a non-positive n, then it holds for 1 less. That inducts down, and so now not only do we have that held for all positive exponents, we now by induction have it holds for all negative exponents as well. And so we have proved in the case that B has an inverse anyway, we have shown that A, B to the, let's say, call it what I put in the theorem statement, A B to the L equals B to the LA for all integers L. Okay, so we now have this. All right, now that we know that powers of B commute with A, and again, if we're just assuming associativity, we can say that for all positive powers L. If we have an identity, we can have all non-negative powers L. And if B is invertible, you don't need that A is invertible yet, but if B is invertible, this holds for all negative powers of B as well. Okay, now, that said, how do I get the full result? Well, it's pretty easy. We have that A commutes with B to the L. So I can apply this result again. That means that any power of A commutes with B to the L. And so that's now true for all K and L. And again, in the specific context where you just have associativity, we would just have this result for positive exponent L, and this would just be for positive exponents K and L. If we have an identity, we get it for non-negative exponents, and if we have inverses for both of them, we can get that. So even more refined things say that as long as either one is invertible, you can apply this to all powers. Right? Okay. That's our lemma. That if things commute, powers commute. And we often use this kind of implicitly in the middle of various work that we do, but it does require proof. Okay, so this is kind of like associativity. Associativity among triples gives you associativity among n things. Well, commutativity among two things is going to give us commutativity among products of those as well. Okay. So here is our last law of exponents. We have that if A and B commute, then AB to the n power is A to the n, B to the n. Okay, but we need that A and B commute to have this particular law of exponents. It's a familiar one, but we need commutativity to make it hold. Okay, proof. Well, as we're used to, we're going to do this by induction. Okay. And so here goes our base case. So the first context, by the way, I'll be working in is just with an associative operation. Again, since it's only two things, alternative would be enough. So we'll do our base case. This would be n equals 1. Well, at n equals 1, there's not really anything to do. This is just by definition. Okay, we don't even need commutativity in that case. So inductive hypothesis. Let's suppose that AB to the n equals A to the n, B to the n for some positive n, okay? And we want to show that it holds for one more. Well, if we take AB to the n plus 1, by definition, that's AB to the n times one more copy of AB. Well, we apply our inductive hypothesis, and we get that that's A to the n, B to the n times AB. Okay. Now we're going to apply our lemma. Our lemma allows us to commute A with a power of B, because now we're using the fact that A and B commute, so A commutes with powers of B. Again, that's using that lemma, and so this becomes A to the n, AB to the n, B. And now we just use definitions to rewrite those as A to the n plus 1, B to the n plus 1. And so finally, by induction, this holds for all n greater than 0. Okay. Now, next case, what if we have an identity? Okay, well, if you have an identity, then we'll change our base case to the 0 power. Okay. There you go. Suppose that this holds for a non-negative n. We get that it holds for 1 power up, and so now it holds for all n greater than or equal to 0. All right, okay. So a slight adjustment there. Okay, well, what if we assume that A and B inverse exist? Okay. So let's assume that we have invertible elements. Okay, well, in that case, we can now show that this goes up and down. Okay, so we have our base case. We now have that this holds for all non-negative exponents. Let's show that it holds for all non-positive exponents. So here we go. Let's suppose that this holds for some non-positive exponent, and we want to go 1 down. Okay. All right, so this now requires a little bit of adjustment. Okay, so we suppose it holds for n. We want to show that it holds for 1 less. And okay, so we apply our inductive hypothesis. We're going to use Sock's shoes to rewrite AB inverse as B inverse A inverse. Okay. Well, which is A to the n, B to the n minus 1. I just used a previously proved law of exponents to combine those B's. Now I'm going to apply my lemma that says that if A and B commute, powers of A and B commute. So I can rewrite that in this way. And then I use my previously proved law of exponents again and get this as A to the n minus 1 times b to the n minus 1. And so we've just shown that if it holds for 0, and if it holds for n, it holds for 1 less. And so by induction, now we have it holds for all non-positive n. And so thus we've inducted up, we've inducted down, and we have that it holds for all integer powers. So this law of exponents, as long as these two things commute, then this law of exponents will hold. And in the case of just an associative operation, this holds for positive exponents. If you have an identity, so 0 makes sense as an exponent, it holds for that. And if these guys have inverses, so that this actually makes sense for negative exponents, it holds for that as well. One maybe little addendum to this, you could ask, does the converse hold? And not quite, but in the case that you have invertible elements, if this holds for n equals minus 1, it will force this to hold. So it's pretty close to having a converse. One other thing to mention is laws of exponents, when we write things additively, look a little bit different. And I thought we would write that down as a kind of final little addendum here. Remember that when you write things multiplicatively, that we write exponents as a superscript. When you write things additively, though, you write exponents as a prefix. So this 3 here is not in the same kind of collection as a belongs to. This is the integer 3 as an exponent. It's an additive exponent. So 3a means add a to itself 3 times. It doesn't mean 3 times a in that context. Okay, what do our laws of exponents say? Well, we had one that said a to the n times a to the m equals a to the n plus m. What does that look like additively? Well, that would be NA plus MA is N plus MA, right? So it looks like a distributive law, but it's really not. That's a law of exponents. And again, if you have just any old operation plus that's associative, this will hold for all positive M and N. If you have an additive identity, which you call 0, when we have a multiplicative identity, we typically call it 1. When you have an additive identity, you call it 0. This is 0, the integer exponent. This is 0, the additive identity, not the same 0. Anyway, if you have an additive identity, this would then hold for M and N possibly being 0 as well, non-negative M and N. Inverses, we write as a superscript here. Additively, we write inverses with negation. And if this exists, then this would hold for all integers. The other law of exponents we have, a to the n to the m power, multiplicatively is a to the m to the n m power, right? That's what this looks like multiplicatively. Additively, this looks like this. Where again, that looks like associativity, but it really isn't. That's a law of exponents where a is in whatever collection you have this additive operation. M and n are integers and they're additive exponents. But it kind of looks like associativity, but it really isn't. That's a law of exponents. It's this law of exponents, but written added for an additive operation. And then finally, if you have AB equals BA, then we have that AB to the n equals A to the n B to the n. Well, if you have A plus B equals B plus A, which generally you don't use addition unless it's commutative, but if you do have that, this law looks like the additive nth power of A plus B is the additive nth power of A plus the additive nth power of B. And again, similar things can be said about if it's just associative, if you have an identity, if you have inverses as to which powers it actually holds for. Okay. And once again, some of these things you could tweak. They will hold in power associative situations or alternative situations where you just have 2 symbols involved. But getting into the ins and outs of those things, that sounds like the topic of another video.